Got no time? Got a test? It's time to cram.
How many times can you fold paper? Let me ask you something. Take a normal sheet of paper and start folding it in half. One fold, two fold, three folds. How many times do you think you can keep going? Most of us have probably tried this experiment, and very quickly the paper becomes so thick and difficult to fold that we simply give up. But here comes the interesting question. Is there really a limit of just 7 or 8 folds? Or is there something much deeper happening here? Today, let's unfold the mathematics hidden inside a simple sheet of paper. And what you are about to see is a perfect example of how mathematics can challenge something we think we already know. The myth versus reality. Your slide introduces the common belief that paper can only be folded 7 to 8 times and then presents Brittany Gallivan's 12-fold achievement. For a long time, there was a popular belief that a sheet of paper could only be folded about 7 or 8 times. And honestly, if you try it yourself with an ordinary sheet of paper, it certainly feels true. After a few folds, the paper becomes thicker, smaller, and much harder to bend. So, people started thinking maybe 7 or 8 folds is simply the limit. But mathematics loves challenging assumptions. In 2002, a high school student named Brittany Gallivan decided to investigate this problem seriously. And she did not stop at 7. She did not stop at 8. She managed to fold a single piece of paper 12 times in a half. That's an important lesson. What looks like a simple physical limitation can actually hide a mathematical pattern. So, now the real question is, why does folding become so difficult? Why there is a limit? Now let's look at the mathematics behind the problem. Every time we fold the paper in half, something very important happens. The number of layers doubles. After one fold, we have two layers. After two folds, four layers. After three folds, eight layers. So the number of layers follows a pattern. 2, 4, 8, 16, 32 and so on. Do you notice what is happening? We are not adding the same number each time. We are doubling each time. And that's exponential growth. Now let's jump all the way to 12 folds. 2 raised to the power of 12 gives us 4096. That means after just 12 folds, we are dealing with 4096 layers of paper stacked together. And this is where the problem becomes really interesting. The paper isn't just becoming thicker, the available width is becoming smaller while the thickness is growing rapidly. Eventually, the folded bundle becomes too thick compared with its remaining width, making another fold extremely difficult. So, Brittany Gallivan's solution wasn't simply to use more force. She changed the size and shape of the paper. She used a roll of tissue paper about 4,000 feet long, roughly three quarters of a mile, and That gives us a beautiful mathematical lesson. Sometimes solving a problem isn't about pushing harder. It's about understanding the mathematics of the problem and changing the strategy. The mathematics hidden in the fold. How does the number of layers grow? To understand this thing, let us make the table. So here we can see that when one fold, then number of layers is 2. Two-fold, then number of layers 4. Three-fold, then layers 8. Four folds, then layers 16. Five folds, then layers 32. And in this way, if we make 12 folds, then the layers are 4096. So therefore, number of layers in general is 2 to the power n. Now let's pause the story for a moment and actually see the mathematics. Imagine we start with just one sheet of paper. After the first fold, we have two layers. Fold it again and those two layers become four. One more fold, then eight layers. Then in this way 16, 32, 64, and in this way we will get 4096 layers by folding 12 folds. Do you notice something? The number of layers is doubling every single time. So instead of adding 2 each time, we are multiplying by 2. And that is the key idea here. After n folds, the number of layers is 2 to the power n. So here 2 to the power n equal to 4096 by 12 folds. And suddenly our simple sheet of paper has turned into a stack containing thousands of layers. This is the power of exponential growth. And here is the fascinating part. We started with just one sheet of paper, but repeated doubling can make the number enormous in surprisingly few steps. That is why this simple folding experiment is actually a beautiful introduction to exponents and exponential growth. Again, I am repeating exponents and exponential growth. But there is an even more interesting question. If the layers are growing so quickly, how large does the paper actually need to be to make more folds possible? Let's find out. Exponents and power. Master the basics. Have you ever seen a multiplication like 5 multiplied by 5 multiplied by 5 multiplied by 5 and thought there must be an easier way to write this? Well, there is. Mathematics give us a very simple and powerful idea called exponents. Exponents allow us to represent repeated multiplication in a short and elegant way. In this lesson, we are going to understand exponents and powers from the very beginning. We will learn what the base and exponent mean, how to write repeated multiplication using powers, how exponents help us with prime factorization, and even how they appear in real life situations. So, let's start with the most basic question. What exactly is an exponent? What are exponents? Let's understand this with a very simple example. Look at 2 to the power 3. We read this as 2 raised to the power 3 or simply 2 to the power 3. Here the number 2 is called a base and the small number 3 written above the 2 is called a exponent. But what does this exponent actually tell us? It tells us how many times the base is multiplied by itself. So 2 to the power 3 means 2 multiplied by 2 multiplied by 2 3 times, and that gives us 8. So remember these three things. Number 1, the large number is the base, the small raised number is the exponent, and the final value is the result or the value of the power. Once you understand this idea, exponents become much easier. In an expression a to the power n, a is the base and n is the exponent or power. Quick reference: a repeated multiplication of the base is known as a note down 5 rules for exponents. Remember, order of operations still applies. Exponents come before multiplication and division. Rules of exponents. First rule: a to the power m multiplied by a to the power n equal to a to the power m plus n. Second rule: a to the power m divided by a to the power n equal to a to the power m minus n. Third rule: a to the power m and bracket complete to the power n equal to the multiplication of both power a to the power mn. Fourth rule: in the bracket ab n to the power n equal to a to the power n multiplied by b to the power n. Fifth rule: in the bracket a divided by b to the power n equal to a to the power n divided by b to the power n. Key idea: what? The exponent tells us how many times the base is used as a factor. Always remember, order of operations still applies. Exponents come before multiplication and division. Expressing repeated multiplication. Now let's see why exponents are so useful. Imagine writing 6 multiplied by 6 multiplied by 6 multiplied by 6. That's perfectly correct, but it's a little long. Since 6 is repeated 4 times, we can write it much more simply as 6 to the power 4. Here is another example. Y multiplied by y becomes y square because y appears twice. Now let's look at something slightly more interesting. 5 multiplied by 5 multiplied by 7 multiplied by 7 multiplied by 7 equal to 5 to the power 2 multiplied by 7 to the power 3. We have two 5's, so we write 5 square, and we have three 7's, so we write 7 to the power 3. Therefore the expression becomes 5 to the power 2 multiplied by 7 to the power 3. The same idea works with variables. For example, if we have two A's and four C's, we write in that way. And answer is a to the power 2 multiplied by c to the power 4. So here is the important rule. Group identical bases together. Count how many times each base appears and use that count as the exponent. That is the basic language of exponents. Prime factorization in exponential form. Now let's take our understanding of exponents one step further. We can use exponents to write the prime factorization of a number in a much more compact form. Let's take the number 32,400. First we break the number down completely into its prime factors. We get several 2's, several 5s and several 3s. Instead of writing every factor separately, let's count them. So these are the factors of 32,400. The prime number 2 appears 4 times, so we write 2 to the power 4. The prime number 5 appears 2 times, so we write 5 to the power 2. And the prime number 3 appears 4 times, so we write 3 to the power 4. Therefore, the prime factorization in exponential form is 2 to the power 4 multiplied by 5 to the power 2 multiplied by 3 to the power 4. Notice the process. First, find the prime factors. Then, group identical factors. Finally, count each group and write that count as an exponent. Exponents are therefore helping us make a long factorization much shorter and easier to read. Powers of negative numbers. Now let's introduce something that often causes confusion. What happens when the base is negative? Look like that. Suppose we have a negative number raised to a power. The answer depends on one important thing. Is the exponent odd or even? Let's first consider an odd exponent. If a negative number is multiplied by itself an odd number of times, the final result is negative. Look like that. For example, negative 1 raised to the power 9 gives a negative result. But what if the exponent is even? Now the negative factors can be paired together. Remember, negative multiplied by negative is always positive. So when we have an even number of negative factors, they form positive pairs. Therefore, an even exponent gives a positive result. So here is the rule you should remember. Negative base with an odd exponent always give negative result. Negative base with an even exponent always gives positive result. But don't just memorize it. Let's verify it with an example. Is minus 2 to the power 4 equal to 16? Let's check whether negative 2 raised to the power 4 really equals 16. Instead of simply trusting the rule, let's calculate it. First, expand the power. Negative to the power 4 means negative product. Now, let's multiply the first pair. Negative 2 multiplied by negative 2 gives positive 4. So now we have 4 multiplied by 4 equal to 16. Therefore, minus 2 to the power 4 equal to 16. And our rule is confirmed. Because the exponent 4 is even, the final answer is positive. Whenever you are confused about a negative base, expand the power and look at the number of negative factors. Special cases, power of 0 and 1. Now let's look at three special cases that are important to remember. First, 0 raised to any positive power. For example, 0 to the power 5 means what? 0 multiplied by itself 5 times. And the answer is simply 0. So, for a positive exponent, 0 raised to any power is 0. Now, comes a special case 0 to the power 0. In the context of this lesson, this is treated as undefined. So don't apply the previous rule blindly here. Finally, let's look at the number 1. 1 raised to any power is always 1. Why? Because multiplying 1 by itself any number of times will always give us 1. So remember, 0 to the power n equal to 0. 0 to the power 0 is undefined in this treatment, and 1 to the power n equal to 1. Calculate numerical values. Now it's time to put everything we have learned into practice. When an expression contains powers along with multiplication, a useful strategy is first evaluate the powers and then perform the multiplication. We know that 10 to the power 3 is 1000. So our final answer is 1000 multiplied by 2 equal to 2000. Now consider 7 to the power 2 multiplied by 2 to the power 3. 7 squared is 49 and 2 cubed is 8 and their product is 392. The same process works for the remaining examples. And notice the last example contains negative numbers. Here we first evaluate each power carefully, paying attention to whether the exponent is odd or even. So don't rush to multiply everything at once. Evaluate the powers first, then multiply. Minus 3 to the power 2 is plus 9 and minus 5 to the power 3 is minus 125 and their final product is minus 1125. The simple strategy helps prevent mistakes. Prime factorization, more examples. Let's now practice writing numbers in exponential form using prime factorization. Take 648 as our first example. We repeatedly divide by the smallest prime possible, starting with 2. Continue dividing until we reach 1. Then we collect all the prime factors we found. If the same prime appears repeatedly, we don't need to write it again and again. Instead, we count how many times it appears and use that number as the exponent. For example, 648 can be written as 2 to the power 3 multiplied by 3 to the power 4. We can follow exactly the same process for 405 as 3 to the power 4 multiplied by 5 to the power 1. 540 as 2 to the power 2 multiplied by 3 to the power 3 multiplied by 5 to the power 1 and 3600 as 2 to the power 4 multiplied by 3 to the power 2 multiplied by 5 to the power 2. Here is a useful habit. Always start with the smallest prime factor and work upward. Then count how many times each prime appears. That count becomes the exponent, right? With practice, you will be able to look at a prime factorization and immediately understand the powers hidden inside it. Paper folding problem. Now let's connect exponents to something we can actually see in the real world. Imagine we have a sheet of paper with an initial thickness of V. What happens when we fold it? After one fold, the number of layers doubles, so the thickness also doubles. After another fold, it doubles again, and this continues with every fold. So after one fold, the thickness is V multiplied by 2. After two folds, After 3 folds, do you see the pattern? After 10 folds, the thickness becomes V multiplied by 2 to the power 10 is always 1024. So, after 10 folds, the thickness is 1024 times the original thickness. This is a beautiful example of exponential growth. A small change repeated again and again can produce a surprisingly large result, and that's exactly why exponents are so useful, not just in mathematics but in understanding patterns in the real world. Key takeaways. Before we finish, let's quickly bring together everything we have learned. First, exponents are a shorthand for repeated multiplication. Instead of writing the same factor again and again, we use a power. Second, remember the rule for a negative base. Odd exponent gives a negative result and even exponent gives a positive result. Third, exponents are extremely useful in prime factorization. They tell us how many times each prime factor occurs. And finally, the best way to become comfortable with exponents is simple. And last, practice makes perfect. Don't just memorize the rules, expand the powers, look for patterns, calculate step by step, and most importantly, understand why the rules work. Once you understand that, exponents and powers stop looking complicated and start becoming a very simple mathematical language. Mathematics becomes easier when you stop memorizing the rules and start seeing the patterns. Keep practicing, keep questioning, and I will see you in the next topic. One pattern hides a lot of multiplication. Let's start with a small puzzle. Imagine there are three daughters. Each daughter has three baskets. Each basket has three keys. Each room has three tables. Each table has three bright necklaces. And each necklace has three diamonds. Can you count these stones that shine? Now, instead of calculating everything one step at a time, let's look at the pattern. At every stage, we are multiplying by 3. So, the total number of diamonds can be represented as that's 7 threes multiplied together. Writing 7 threes every time is a little lengthy. So, mathematics gives us a shortcut. The small number 7 tells us exactly how many times 3 is being used as a factor. And this is the basic idea behind exponents. Repeated multiplication can be written in a much shorter form using powers. Now, let's understand the two numbers inside a power and what each one is telling us. So, when you see something like 5 to the power 3, don't just look at it as a number. Let's learn how to read what each part is saying.
Imagine a massively wealthy king who organizes his royal treasury in this incredibly complex, cascading way. Okay, so the king has three daughters. Each of those daughters has exactly three baskets. Inside each basket, three keys. Each key opens one of three rooms. Inside each room, there are exactly three tables. On every single table, three bright necklaces. And finally, on every single necklace, there are exactly 3 diamonds. So, how many diamonds are there in total? I mean, just thinking about counting those one by one is absolutely exhausting, right?
Right, because look at this branching cascade. From the daughters, down to the baskets, all the way down to those tiny diamonds. To actually find the total, you'd have to multiply 3 times 3 times 3 times 3 times 3 times 3. Writing out 3 times itself 7 times over is just tedious. It takes up a ton of space. And honestly, it leaves a massive amount of room for silly errors. And that brings us to the lazy mathematician's brilliant solution. Just write it as 3 to the power of 7. Boom.
Base and exponent work as a team.
Okay, let's look at our roadmap for today. We'll start with the anatomy of a power, then evaluating powers, multiplying identical bases, figuring out the power of a power, dodging common traps, and finally an exit check to see what's stuck.
Take a look at 5 to the power 3. There are two important numbers here and each has a different job. The larger number 5 is called a base. The base is the number that is being multiplied repeatedly. The small raised number 3 is called the exponent. The exponent tells us how many times the base appears as a factor. So 5 to the power 3 means 5 multiplied by 5 multiplied by 5, and when we calculate it we get 125. We can read 5 to the power 3 as 5 cubed. But here is something very important. The exponent 3 does not mean that we multiplying 5 by 3. In other words, 5 to the power 3 is not a 5 multiplied by 3. Instead, it means that 5 is used as a factor 3 times. So, remember, base tells us what number is repeated. Exponent tells us how many times it is repeated. Once these two work together, we have a power. Now that we know how to read a power, let's see how we can convert ordinary multiplication into this compact form. So for that, express the following in exponential form in your homework.
If we look at the expression 5 to the third power, also called 5 cubed, the number 5 is our base. Think of the base as the one doing all the heavy lifting. It's the actual number being multiplied. Then, that tiny 3 sitting up top, that's the exponent. The exponent is basically the supervisor, just telling the base how many times it needs to show up for work. So 5 to the third power literally just means 5 shows up 3 times. 5 times 5 times 5.
Now, we've got to destroy the absolute most common trap right away. Look really closely at this comparison. An exponent counts repeated factors. It absolutely does not mean you just multiply the big number by the small number. 5 to the third power is 5 times 5 times 5, which gets us 125. It is definitely not 5 times 3, which is just 15. Seriously, locking down this single distinction will save you on like 90% of your early math tests.
Turn products into powers. Now let's reverse the process. Suppose I give you 6 multiplied by 6 multiplied by 6 multiplied by 6. The first thing you should do is look for identical factors. Here the number 6 appears 4 times. So we can write it as 6 to the power 4. Let's try another one. Y multiplied by y. The base is y and it appears twice. So we write y square. Now look at 2 multiplied by 2 multiplied by a multiplied by a. There are two 2's and two a's. So we write 2 to the power 2 and a to the power 2. Notice that different bases remain separate. We don't mix the 2's and the a's together. Here is another example. 5 multiplied by 5 multiplied by 7 multiplied by 7 multiplied by 7. There are two 5's, so we write 5 to the power 2. There are three 7's, so we write 7 to the power 3. Therefore, 5 to the power 2 multiplied by 7 to the power 3. So the method is simple. First, identify identical factors. Second, count how many times each one appears. Third, use that count as the exponent. Different bases get their own powers, but writing a power is only half the story. We also need to know how to calculate its value correctly. Here the homework for you. Write the numerical value of each of the following. Evaluate powers carefully. When we need to calculate the value of a power, let's follow a simple two-steps method. Step 1. Expand the power. That means rewriting the power as repeated multiplication. For example, if we have 10 to the power 3, we know it means. Then we calculate. So 10 to the power 3 is 1000. If we have 2 multiplied by 10 to the power 3, we first evaluate 10 to the power 3 as a 1000. That gives us 2000. Similarly, for 7 to the power 2 multiplied by 2 to the power 3, we calculate the powers first. 7 to the power 2 is 49 and 2 to the power 3 is 8. Therefore, 49 multiplied by 8 equal to 392. Now there is one more thing we need to be very careful about: parentheses. Look at minus 3 to the power 2. The parentheses tell us that the entire negative 3 is the base. So we have minus 3 multiplied by minus 3 is equal to plus 9. The parentheses matter because they tell us exactly what the exponent is acting on. So whenever negative numbers and powers appear together, slow down and check the parentheses. Now we are ready for something really powerful: using exponents to simplify multiplication. Multiplying same bases, add the exponents. Here is one of the most useful rules of exponents. Suppose we multiply two powers with the same base. For example, p to the power 4 multiplied by p to the power 6. Let's expand it. P to the power 4 means 4 p's multiplied together, and p to the power 6 means 6 more p's multiplied together. So altogether, how many p's do we have? 4 plus 6 gives us 10 p's. Therefore, p to the power 4 multiplied by p to the power 6 equal to p to the power 10. And that gives us our rule: a to the power m multiplied by a to the power n is equal to a to the power m plus n. In simple words, when the bases are the same, add the exponents. For example, 3 to the power 2 multiplied by 3 to the power 5 is equal to 3 to the power 7, because 2 plus 5 equal to 7. But there is an important condition: we can add the exponents only when the bases are identical. So don't look at every multiplication problem and automatically add the exponents. First, ask yourself, are the bases the same? If yes, we can use this rule. Now, let's look at a different situation. What happens when one power is raised to another power? Do notice this. A power of a power. Multiply the exponents. Now we have a different structure. Look at a to the power m bracket complete to the power n. Here We have a power raised to another power. The key is to understand what the other exponent is doing. The exponent n tells us that the entire expression a to the power m is being used as a factor n times. So, instead of adding the exponents, we multiply them. Therefore, a to the power m bracket complete to the power n equal to a to the power mn. Let's take the example on the slide. 4 to the power 2 bracket complete to the power 3 is equal to what? The outer exponent is 3. So 4 to the power 2 is repeated 3 times. That means 4 to the power 2 multiplied by 4 to the power 2 multiplied by 4 to the power 2. Since the bases are now the same, we have three groups of 4 to the power 2. So we get 4 to the power 6. And notice where the 6 came from. By 2 multiplied by 3 equal to 6. So the rule is power of a power multiply the exponents. This is different from the previous rule, same base multiplication add. Power of a power multiply. Don't mix these two rules. Now homework for you. Write the following expression as a power of a power in at least two different ways. Now let's see if you can identify which rule to use without me telling you. So, what you know? Now it's your turn. Let's see whether you can use the ideas we have just learned. First, look at 8 to the power 6, 7 to the power 15, and 9 to the power 14. Your challenge is to write each one in at least two different ways as a power of a power. Don't rush to calculate the actual values. Instead, focus on understanding the relationship between the exponents. Next, try rewriting 2 to the power 10 as a 2 to the power 5 bracket complete to the power 2. Now ask yourself, why does this work? Because when we have a power raised to another power, we multiply the exponents. 5 multiplied by 2 gives 10 here. Now let's finish with our quick exit check. What is x to the power 3 multiplied by x to the power 4? Same base? Yes. So what do we do? Add the exponents. Therefore the answer is x to the power what? 7. And what about y to the power 2 bracket complete to the power 5? This is a power of a power. So we multiply the exponents to multiply with 5 gives 10. Therefore the answer is y to the power 10. So before you finish, remember these two golden rules. First, same base add exponents. Second, power of a power multiply exponents. If you can identify the structure of the expression, choosing the correct rule becomes much easier. And then complete the given homework for you. Magical pond. One day changes everything. Let's begin with a little mystery. Imagine you are watching a pond covered with beautiful lotus plants. Every single day the number of lotus plants doubles. On day 30, something surprising happens. The entire pond is covered. Now here is my question for you. On which day was the pond exactly half covered? Take a moment and think about it. Don't calculate forward from day 1. Instead, let's think backwards. If the number of lotuses doubles every day, then the number on day 30 must be twice the number on day 29. So, if day 30 represents 2 to the power 30 lotuses, then day 29 must represent 2 to the power 29 lotuses. And that is exactly half of the day 30 amount. So, the answer is what? Day 29. This is a beautiful example of exponential growth. And notice something interesting. The pond did not become half full several days before day 30. It was exactly half full just one day earlier. That is how quickly exponential growth can change a situation. Now, let's extend the idea. If day 1 has one lotus, can you express the number of lotuses on day 4 and day 10 as a power of 2? Look for the pattern. So, doubling gives us powers of 2. But what if the number doesn't double? What if it triples every day? Triple the lotuses exponents compress repeated multiplication. Let's change the story. This time imagine the number of lotuses triples every day instead of doubling. After 4 days, the growth can be represented by 3 to the power 4. Now, suppose we continue for another 4 days, we would have 3 to the power 4 multiplied by 3 to the power 4. Since the bases are the same, we can combine these powers. 4 factors of 3 here and another 4 factors of 3 here. So altogether we have 8 factors of 3. Therefore, 3 to the power 4 multiplied by 3 to the power 4 equal to 3 to the power 8. And 3 to the power 8 is 6561. So a relatively simple repeated growth process has already produced thousands of lotuses. Now let's turn this into an activity. Imagine you have cards showing different powers. Your job is to find cards with the same base and merge them. For example, 3 to the power 4 and 3 to the power 4 becomes 3 to the power 8. What rule did we just discover? A to the power m multiplied by a to the power n equal to a to the power m plus n. In simple words, when multiplying powers with the same base, add the exponents. We have seen what happens when we multiply powers. Now let's see what happens when we divide them. One rule, three representations. Now let's look at division involving powers. Consider 10 to the power 4 divided by 5 to the power 4. One approach would be to calculate both large powers first. But do we really need to? Look carefully. Both numbers have the same exponent, which is 4. So we can use the exponent rule. A to the power m divided by b to the power m is equal to, in the bracket, a divided by b bracket complete to the power m. That means 10 to the power 4 divided by 5 to the power 4 can be written as, in the bracket, 10 divided by 5 bracket complete to the power 4. 10 divided by 5 is 2. So we get 2 to the power 4. And finally 2 to the power 4 equal to 16. Notice what we avoided. We did not have to calculate 10 to the power 4 and 5 to the power 4 separately. We simplified the expression first. That is one of the biggest advantage of exponent laws. They allow us to simplify first and calculate later. Now here is your challenge. Can you simplify 10 to the power 4 divided by 5 to the power 4 without calculating either large power, and after that match the three forms: quotient form, exponential form, and numerical answer. The goal is not just to get 16. The goal is to understand why all three representations are equivalent. So far, we have counted repeated growth, but multiplication can also help us count something much more familiar: different choices. Here is a homework for you. Simplify 10 to the power 4 divided by 5 to the power 4 and write in exponential form. Dress up lab. Every cape meets every dress. Now let's move away from numbers for a moment and think about clothing. Imagine you have four different dresses and three different capes. How many different outfits can you create if you choose one dress and one cape? Let's now guess. Take the first dress. It can be paired with all three capes. So the first dress gives us three outfits. The second dress also gives us three outfits. The third gives us three. And the fourth gives us another three. So we could think of this as 3 plus 3 plus 3 plus 3. But repeated addition can be written as multiplication. 4 multiplied by 3. Therefore, we have 12 different outfits. We can also visualize this using a tree diagram. Each dress creates three branches, one for each cape. This is an important counting idea. When every choice from one group can be paired with every choice from another group, we multiply the number of choices. Before you actually pair the cards, try to predict the answer, then verify it. Now let's make the problem a little more interesting by adding one more choice. Roxy's outfit code. Add shoes to the product. Our outfit problem is getting bigger. This time Roxy has 7 dresses, 2 hats and 3 pairs of shoes. Let's think about the choices step by step. First, choose a dress. There are 7 possibilities. For every dress we can choose either of the two hats, and for every dress and hat combination we have three choices of shoes. So the total number of outfit is 7 multiplied by 2 multiplied by 3. That gives us 42 different outfits. Notice how the multiplication principle works. We multiply the number of choices at each stage. Now let's change one thing. Suppose one of the heads disappears. We now have only one head. So our calculation becomes 7 multiplied by 1 multiplied by 3 equal to 21. The number of possible outputs has dropped from 42 to 21. That's exactly half. So here is something powerful to notice. Changing the number of choices at even one stage can change the total number of possibilities. This same idea appears in many places beyond clothing, and that is where our next mystery takes us. The safe mystery. How many passwords must they test? Now let's apply the same counting principle to something we encounter in technology: passwords. Imagine a lock that uses 6 digits. For each position We can choose any digit from 0 to 9. That is 10 choices for each position. Since there are 6 positions, the total number of possibilities is 10 to the power 6, and that equals 1 million possible passwords. Now imagine a different lock using 6 letters. If we use the 26 letters of the alphabet, each position has 26 choices. So the total becomes 26 to the power 6. That is 308,915,776 possible passwords. Now, before accepting any answer in a counting problem, there is something very important we must ask. What assumptions are we making? Is repetition allowed? Are leading zeros allowed? These details can completely change the answer. So, don't just calculate. Read the conditions carefully first. That is an essential mathematical habit. Now let's see how dramatically the number of possibilities changes when we replace just a few digits with letters. 5 characters, 2 words or possibilities. Let's compare two 5-character passwords. First, imagine all 5 positions use digits. Each position has 10 choices. So the total number of possibilities is 1 lakh combinations. Now let's replace those digits with letters. Each position now has 26 choices. So we get 26 to the power 5, and answer is 11,881,376 combinations. Look at the difference. We change the number of choices at each position from 10 to 26, and the total number of possibilities increased dramatically. Look, this is where exponents and counting work together. We can actually build a simple password machine to see this happen. Start with 5 columns. Give each column Give each column 10 choices. Now change one column from digit to letters. Then change another each time the number of choices changes. Watch what happens to the total. You are not just calculating numbers, you are watching the number of possibilities grow. And that is the key question. How quickly can possibilities grow when we have multiple choices at multiple positions? Code detective. Where do we use combinations? Now, it's time to become a code detective. Look around the real world. We use many different kinds of codes. Some contain only digits, such as pin codes. Some may use letters, and some are mixed using both letters and numbers. Your challenge is to investigate these different types of codes. For each code, ask yourself how many choices are available at each position. Then ask how many positions are there. Once you know those two things, you can represent the total number of possibilities using multiplication or an exponent. For example, if there are 10 choices for each 5 positions, we can write 10 to the power 5. If there are 26 choices for each of 5 positions, we write 26 to the power 5. And if different positions have different numbers of choices, we multiply those choices together. So, here is your final challenge. Explain one sentence why the same big idea works for outfits, passwords, and codes. The answer is this. We count the choices available at each stage and multiply them together. That is the common mathematical idea hiding behind all three situations. Negative and zero exponents. Rule number 1. Subtract exponents when dividing. Let's begin with one of the most useful rules of exponents. What happens when we divide two powers that have the same base? Suppose we have n to the power a divided by n to the power b. When the bases are the same, we can subtract the exponents. So n to the power a divided by n to the power b is equal to n to the power a minus b. But why does this work? Let's look at an example. Consider 2 to the power 100 divided by 2 to the power 25. Think of the numerator as 100 factors of 2. The denominator contains 25 factors of 2. Look at here. That leaves us with 75 factors of 2. So 2 to the power 100 divided by 2 to the power 25. So subtraction of the exponent is equal to 2 to the power 75. That's why the rule works. We are not simply memorizing a subtraction rule. We are actually counting how many factors remain after cancellation. So remember, same base and division, subtract the exponent. Now let's ask a very interesting question. What happens if the two exponents we subtract are exactly the same? Rule number 2. Any non-zero number to power 0 is equal to 1. Now let's take our previous rule one step further. What happens when we divide a power by the exact same power? For example, x to the power a divided by x to the power a. Since the bases are the same, we subtract the exponents. So we get x to the power 0. But we also know something else. Any non-zero number divided by itself is 1. For example, 5 divided by 5 is 1. 10 divided by 10 is 1. And x divided by x is 1 as long as x is not 0. Therefore, x to the power 0 equal to 1. So any non-zero number raised to the power 0 equals 1. For example, 2 to the power 0 equal to 1 and 100 to the power 0 equal to 1. And even a negative non-zero number raised to the 0 power is 1. But there is one important condition. The, the base cannot be 0. Division by 0 is not defined. So always remember the condition along with the rule. Also consider this slide. Now we know what happens when the exponent reaches 0. But what happens when we go one step further and the exponent becomes negative? A negative exponent means reciprocal. This is where negative exponents become interesting. Let's start with something we already know. 10 to the power 0 equal to 1. Now imagine we move one step backward in the exponent pattern. What should 10 to the power minus 1 be? Remember our division rule. Every time the exponent decreases by 1, we are effectively dividing by the base. So from 10 to the power 0 equal to 1. Moving to 10 to the power minus 1 means dividing by 10. Therefore, 10 to the power minus 1 is equal to 1 upon 10. Move one more step. 10 to the power minus 2. Then minus 2, then we have to divide by 100, means 2 0. Minus 2, number 2, so 2 0. So 1 by 100. This mechanism we have to remember. And another 10 to the power minus 3, 1 upon 1000. So a negative exponent does not mean the answer becomes negative. Instead, it tells us to take the reciprocal. Therefore, the general rule is n to the power minus a is equal to 1 upon n to the power a. For example, 10 to the power minus 3 is equal to 1 upon 10 to the power 3 is equal to 1 upon 1000. So, whenever you see a negative exponent, think, flip it to the denominator and make the exponent positive. Now, you may be wondering, do these exponent laws still work when the exponents themselves are negative or zero? Do practice this slide. Rule number 4. The rules also work for integer exponents. The good news is that the exponent laws don't suddenly stop working when we introduce zero or negative exponent. The same laws continue to work for integer exponents. That includes positive numbers, zero, and negative exponents. There is one important condition: the base must not be zero. Let's look at an example: 5 to the power 2 divided by 5 to the power 5. Since the bases are the same, we subtract the exponent. So 5 to the power 2 minus 5. Now we have a negative exponent, so we use our negative exponent rule. 5 to the power minus 3 is equal to 1 upon 5 to the power 3. Therefore, 5 to the power 2 divided by 5 to the power 5 is equal to 1 upon 5 to the power 3. Notice how the rules work together. First, we subtract the exponents, then look, then because the exponent is negative, we rewrite it as a reciprocal. That's the power of understanding the rules instead of memorizing isolated formulas. Let's now practice converting negative powers into ordinary fractions. Rewrite each negative power. Let's make negative exponent easier to handle. Whenever you see a negative exponent, remember one simple action: move the base to the denominator and change the exponent to positive. For example, 2 to the power minus 5 becomes 1 upon 2 to the power 4, and 2 to the power 4 is 16. So the answer is 1 upon 16. Similarly, 10 to the power minus 5 is equal to 1 upon 10 to the power 5 is equal to 1 upon 1 lakh. Now let's look at a negative base. Minus 7 to the power minus 2. The entire base is negative 7. So we get 1 upon minus 7 to the power plus 2. Since the exponent is even, the denominator becomes positive and the final answer is 1 upon 49. Also, this we learnt earlier. But look at minus 5 to the power minus 3. The exponent is odd, so the denominator remains negative. Minus 5 to the power minus 3 is equal to 1 upon minus 5 to the power plus 3, and final answer is equal to minus 1 upon 125. And here is a very important point. A negative exponent does not mean a negative answer. It tells us to take the reciprocal. The sign of the answer still depends on the base and whether the exponent is odd or even. In this way, do the homework for last sum. In this way, do notice the sum 10 to the power minus 100, and the answer is 1 upon 10 to the power 100. A negative exponent does not make the answer negative. Now let's combine negative and positive exponents in the same multiplication problem. Combine powers by adding exponents. Now let's put our exponent rules together. Remember, when multiplying powers with the same base, we add the exponents. This rule still works even if one of the exponents is negative. Let's take 2 to the power minus 4 multiplied by 2 to the power 7. The bases are the same, so we add the exponent as a minus 4 plus 7 equal to, therefore 2 to the power 3 equal to 8. Let's try another. 3 to the power 2 multiplied by 3 to the power minus 5 multiplied by 3 to the power 5. Since all the bases are 3, we add the exponents, and the answer is 3 to the power 2 equal to 9. And here is another interesting example. P to the power 3 multiplied by p to the power minus 10 is equal to p to the power minus 7, and after converting it into the positive power, we will get 1 upon p to the power 7. The important idea is that the same exponent law continues to work. Positive exponent, zero exponent, or negative exponent, the structure of the rule remains the same. But there is another way to understand all of this without memorizing every step. We can actually visualize exponents on a number line. Look here. Two more examples also given here. 2 to the power 4 multiplied by minus 4 to the power minus 2. So 2 to the power 4 is evaluated as 16, and minus 4 to the power minus 2 is evaluated as 1 upon 16, and final answer is 1. Same way, the next example, 8 to the power p multiplied by 8 to the power q is equal to 8 to the power p plus q. Power lines make exponents visible. Let's imagine the powers of 4 as a number line. Start with 4 to the power 1 equal to 4. If we move one step upward, we multiply by 4. So 4 to the power 2 equal to 16. Move up again. 4 to the power 3 equal to 64. And again 4 to the power 4 is equal to 256. So moving upward means multiply by 4. Now let's travel in the opposite direction. From 4 to the power 1, move one step down. So 4 to the power 0 equal to 1. Move down again. 4 to the power minus 1 equal to 1 upon 4. One more step, 4 to the power minus 2 is equal to 1 upon 16. Suddenly negative exponents don't look mysterious anymore. They are simply the continuation of the same pattern. Every time the exponent increases by 1, we multiply by 4. Every time the exponent decreases by 1, we divide by 4. This power line is a very useful way to see exponent rules instead of just memorizing them. Do notice this explanation. Now let's use exponent rules to compare two powers and find out how many times larger one is than the other. Rule number 8. Compare powers by dividing them. Suppose someone asks, how many times larger is 4 to the power 7 than 4 to the power 5? The phrase how many times larger gives us a clue. We need to divide the larger quantity by the smaller one. So we write 4 to the power 7 divided by 4 to the power 5. The bases are the same, therefore subtract the exponent 4 to the power 7 minus 1 and 4 to the power 2 equals to 16. So 4 to the power 7 is 16 times 4 to the power 5. So 4 to the power 7 is 16,384 is 16 times larger than 4 to the power 5 means 1024. Notice how efficiently we solved this. We didn't need to calculate 4 to the power 7 and 4 to the 4 to the power 5 separately. We simply compared their exponents. That's another advantage of exponent laws. They let us compare very large numbers without actually calculating those large numbers. Let's take this idea further by expressing ordinary numbers as powers of the same base. Rule number 9. Use the power line of 7. Now we are going to use the power line of 7. The key is to recognize familiar numbers as powers of 7. For example, 7 to the power 2 equal to 49. Or, or else we can say 49 equal to 7 to the power 2. Same way 343 is 7 to the power 3. 2401 is 7 to the power 4 and 16,807 is 7 to the power 5. Once we rewrite the numbers using the same base, many calculations become much easier. Let's look at 2401 multiplied by 49. Replace each number with its power of 7. Look, 2401 is what? Look the power line. 7 to the power 4 and 49. 7 to the power 2. Same base, so add the exponents and answer is 7 to the power 6, which equals 117649. Now look at 16,807 divided by 49. That is 7 to the exactly what? Is 7 to the power 5 divided by 7 to the power 2. Subtract the exponents, then you will get 7 to the power 3 is equal to 343. And here is an interesting one. Is 7 divided by 343. That is 7 to the power 1 divided by 7 to the power 3 is equal to 7 to the power minus 2. And a negative exponent tells us to take the reciprocal. So we will get a 7 to the power minus 2 as a 1 upon 49. Do notice this all calculations. Pause the video and do notice the calculation. So the strategy is simple. Rewrite everything using the same base, then apply the exponent law. Once the common base becomes visible, the calculations become much easier. Now let's finish with a comparison involving a positive exponent and a negative exponent. How many times larger than 4 to the power minus 2 is 4 to the power 2? So rule number 10, 4 to the power 2 is 256 times larger than 4 to the power minus 2. Let's finish with a very interesting comparison. How many times larger is 4 to the power 2 than 4 to the power minus 2? Remember, whenever we ask how many times larger, we divide the larger quantity by the smaller one. So we write 4 to the power 2 divided by 4 to the power minus 2. The bases are the same, so we subtract the exponent. Be careful here. We have 2 minus negative 2. Subtracting a negative becomes addition and we will get a plus 4. So 4 to the power 2 divided by 4 to the power minus 2 is equal to 4 to the power 4 and 4 to the power 4 is equal to 256. So 4 to the power 2 is 256 times larger than 4 to the power minus 2. This example beautifully connects everything we have learned: same base division, negative exponents, subtracting negative numbers, and comparing powers. And notice something fascinating: positive and negative exponents are not separate ideas, they are all part of one continuous pattern. Let's take a moment to see the bigger picture. We started with a simple rule for dividing powers. Same base, subtract the exponents. From that idea, we discovered why any non-zero number raised to the power 0 is 1. Then we understood that a negative exponent represents a reciprocal. We learned how to combine positive and negative exponents, visualize them on a power line, and compare very large and very small powers efficiently. The most important thing is not to memorize 10 separate rules. 10 separate rules. Instead, instead, understand the pattern behind them. When the structure makes sense, the rules become natural, and that is the real power of exponents. Powers of 10 expanded form. Okay, students, let us begin with a very important idea: expanded form using powers of 10. Look at the number 172. We know that 172 means 100 plus 70 plus 2. But today we are going to write the same number in a more mathematical way using powers of 10. The 1 is in the 100 place, so we write 1 multiplied by 10 to the power 2. The 7 is in the 10th place, so we write 7 multiplied by 10 to the power 1. and the 2 is in the ones place, so we write 2 multiplied by 10 to the power 0. So 172 equal to 1 multiplied by 10 to the power 2 plus 7 multiplied by 10 to the power 1 plus 2 multiplied by 10 to the power 0. Now look at 5642 and 6374. Can you identify which power of 10 belongs to each digit? Remember our simple rule. Place value equal to digit multiplied by corresponding power of 10. So same way 5 is in the thousands place, so we write 5 multiplied by 10 to the power 3 plus 6 multiplied by 10 to the power 2 plus 4 multiplied by 10 to the power 1 plus 2 multiplied by 10 to the power 0. And same way for 6374 we can write. Keep this rule in mind because we are going to use it throughout this lesson. Decimal numbers in expanded form. Now, let's make this idea a little more interesting. What happens when the number contains a decimal point? Take the number 561.903. For the whole number part, nothing changes. 5 is in the hundred place as 5 multiplied by 10 to the power 2. 6 is in the tens place as 6 multiplied by 10 to the power 1. 1 is in the ones place as 1 multiplied by 10 to the power 0. But now look at the decimal part. The 9 is in the tens place, so its power is 10 to the power minus 1. The 0 is in the hundreds place, so we write 10 to the power minus 2. And the 3 is in the thousands place, so we use 10 to the power minus 3. So the decimal point takes us into negative powers of 10. This is a very important connection. Whole number places positive or zero powers. Decimal places negative powers. So expanded form is not just for whole numbers, it works beautifully with decimals too, large numbers and scientific notation. Now let's move from ordinary numbers to very large numbers. Do notice this slide. Imagine writing a number with many zeros. It becomes difficult to read and difficult to calculate. That is where scientific notation becomes extremely useful. The rule is simple. We move the decimal point until the number in front of the multiplication sign is at least 1 but less than 10. For example, 1,42,395 becomes 1.42395 multiplied by 10 to the power 5. Why 10 to the power 5? Because we moved the decimal point 5 places. And look at another useful connection. 1 lakh equal to 1 multiplied by 10 to the power 5. Similarly, 40,000 equal to 4 multiplied by 10 to the power 4. So, scientific notation gives us a very compact way to represent large numbers. Whenever you see a huge number, ask yourself, can I express this using a number between 1 and 10 multiplied by a power of 10? The Sun, Earth and Saturn. The Sun-Earth distance is the smallest. Now, let's see why scientific notation is actually useful in real life. We are going to compare distances in our solar system. The distance from the Sun to Earth is approximately 1.496 multiplied by 10 to the power 11 meters. The distance from Earth to Saturn is around 1.2 to 1.4 multiplied by 10 to the power 12 meters. And the distance from the Sun to Saturn is approximately 1.4335 multiplied by 10 to the power 12 meters. Now look carefully at the powers of 10. We have 10 to the power 11 and 10 to the power 12 because 10 to the power 12 is 10 times larger than 10 to the power 11. We can immediately understand the scale of these enormous distances. In fact, Earth is only about 10.4% of the Sun to Saturn distance. Along this comparison, so this is the real power of scientific notation. It allows us to compare enormous quantities quickly without writing endless zeros. Practice scientific notation. Numbers in scientific notation. Now it's your turn to become the mathematician. Let's convert these numbers into scientific notation. First, 59,853. Move the decimal point until we get a number between 1 and 10. We get 5.9853 multiplied by 10 to the power 4. Next, 65,950 is equal to 6.595 multiplied by 10 to the power 4. Next, look at 34,30,000. We get 3.43 multiplied by 10 to the power 6. 70 crore 4 lakh becomes 7.004 multiplied by 10 to the power 8. Notice the pattern. The number of places we move the decimal point tells us the power of 10. So, whenever you are converting a number into scientific notation, don't just memorize the answer. Count the decimal point movements. Real life application section. Estimating the value of donated food. Now we are going to apply mathematics to a real life situation. Suppose Roxy and Estu decide to donate food and the value of the donation is related to their weight. How can we calculate the value? The basic mathematical relationship is value equal to quantity multiplied by price per unit. So, for Roxy, weight in kilograms multiplied by price of jaggery per kilogram, and for S2, weight in kilograms multiplied by price of wheat per kilogram. But there is something very important here. The problem doesn't give us all the information we need. So, we have to make reasonable assumptions. And whenever we make assumptions in mathematics, we must clearly mention them. That is an important mathematical skill, not just getting the answer, but explaining how we arrived at the answer. Calculating the donation value. Now, let's put our assumed values into the calculation. For Roxy, let's assume her weight is 45 kilograms and jaggery costs 70 rupees per kilogram. So 45 multiplied by 70 equal to 3150 rupees. Therefore the value of Roxy's jaggery donation is rupees 3150. For S2, let's assume a weight of 50 kilograms and wheat costs rupees 50 per kilogram. So 50 multiplied by 50 equal to rupees 2500. Therefore, S2's wheat donation is worth rupees 2500. Notice how a simple multiplication calculation helps us solve a real world problem. How many rupees one coin? So next topic is how many 1 rupee coins equal the jaggery's value. Now here is an interesting question. Roxy's jaggery donation is worth rupees 3150. Imagine that instead of paying this amount using notes, we want to represent the same value using 1 rupee coins. How many coins would we need since every coin is worth exactly rupees 1? So rupees 3150 divided by rupees 1 equal to 3150 coins. So we would need exactly 3150 1 rupee coins. This is a great example of how division helps us answer a practical question. Now let's think, is 3150 a small number, a hundreds number, or a thousand number? Let's find out on the next slide. Classifying 3150 coins. Let's locate 3150 on our number scale. We know hundreds range from 100 to 999. Thousands range from 1000 to 9999. Ten thousands begin from 10,000. So where does 3150 belong? Exactly in the thousands. It is greater than 1000 but less than 10,000. And if we compare it with 3000 and 4000, we can see that 3150 is much closer to 3000. So we are not just reading a number, we are understanding its size and position. This is an important estimation skill, estimating the weight of the coin. Now comes a fascinating estimation question. We have 3151 rupee coin. How heavy would all these coins be? For our classroom estimation, let's assume that one coin weighs approximately 5 grams. So 3150 multiplied by 5 is equal to 15,750 grams. Now convert grams into kilograms since 1000 grams equal to 1 kilogram. So 15,750 grams equal to 15.75 kilograms. So our estimated total weight is approximately 15.75 kilograms. And here is an important mathematical lesson. When we estimate, we must clearly state our assumption. The actual weight of a coin can be checked experimentally by weighing a known number of coins and dividing the total weight by the number of coins. That is how mathematics connects with measurement and experimentation. Estimating annual offerings. Let's finish with one more real life estimation problem. Here we have to make assumptions because the exact quantities aren't specified. For Roxy, we interpret 45 kilograms as 45 notebooks donated per year. If one notebook goes to one student, approximately 45 people could benefit. For S2, suppose 50 kilograms of grain is donated. If one serving requires 0.2 kilograms, then 50 divided by 0.2 equal to 250 servings. So, approximately 250 people could receive one serving. And this brings us to an important mathematical habit. Whenever a problem involves estimation and the information is incomplete, clearly state your assumptions. Remember, in estimation problems, the reasoning is just as important as the final answer. Excellent work. We have connected powers of 10, extended form, scientific notation, estimation, measurement, and real life applications in one lesson. Today we are going to explore two very different ways in which quantities can grow: linear growth and exponential growth. Let's imagine something very simple. Suppose a ladder becomes one step longer every day. If today it has 5 steps, tomorrow it has 6, then 7, then 8. We are adding the same amount each time. This is linear growth. But now imagine a quantity that keeps doubling: 2, 4, 8, 16 up to infinity. Here we are not adding the same number, we are multiplying by the same factor. That is exponential growth. And the interesting part is this: exponential growth may start slowly, but very quickly it can become enormous. Today we are going to use real life examples to understand this difference and also see how powers of 10 and scientific notation help us deal with extremely large numbers. How many 20 centimeter steps reach the moon? Let's begin with a question that sounds almost impossible. Imagine that you could walk all the way from Earth to the moon, and every step you take is exactly 20 centimeters. How many steps do you think you would need? Would it be thousands? Maybe lakhs? Crores? Take a few seconds and make your own estimate before we calculate. The moon is approximately 3,84,400 kilometers away, but our step is measured in centimeters. So we first need to convert the distance. 3,84,400 kilometers becomes 384,400,000 meters. And finally, the large digit shown in the slide as centimeters. Now divide this distance by 20 centimeters per step. That gives us 1922,000,000 steps. In scientific notation, that is approximately 1.92 multiplied by 10 to the power 9 steps. So we are talking about nearly 2 billion steps. This is a perfect example of why scientific notation is useful. Instead of struggling with a huge string of zeros, we can describe the size of the number using a power of 10. Before revealing the answer, who estimated closest to the actual answer? Tell me in comment box. Can you come up with some example of linear growth and of exponential growth? Find growth in everyday life. Now let's bring growth into our everyday lives. Suppose I save rupees 100 every week. My savings would look like this: 100, 200, 300, 400 rupees and so on. What am I doing each time I am adding rupees 100? So, this is linear growth. Here is another example. Suppose I read 2 additional pages every day as 2, 4, 6, 8 and so on. Again we are adding the same amount. Now let's change the situation. Imagine a population of bacteria that doubles every hour. We get 1, 2, 4, 8, 16 and so on. Look carefully. Here we are multiplying by 2 each time. That is exponential growth. And this is where exponential growth becomes fascinating. In linear growth, we keep adding the same amount. In exponential growth, the amount being multiplied is itself getting larger. So the growth becomes faster and faster. Now I want you to look at the examples on the screen and decide, is this linear growth or exponential growth? 1 power of 10 can describe huge populations. Now we are going to see real power of powers of 10. Look at 10 to the power 9. This means 1 followed by 9 zeros. That is 1 billion. Now imagine trying to count quantities that are much larger than this. There are about 8 billion humans on Earth. There may be around 10 billion chickens worldwide, and the estimated number of ants can be around 10 to the power 16. We can even use powers of 10 to describe incredibly large astronomical quantities. For example, the number of stars in the universe is estimated on an enormously large scale. The important idea is not memorizing all these numbers. Instead, look at the exponent. The exponent immediately tells us about the scale of the number. For example, compare 10 to the power 12 and 10 to the power 15. 10 to the power 15 is much larger. In fact, 10 to the power 15 divided by 10 to the power 12 equal to 10 to the power 3 equal to 1000. So, 10 to the power 15 is 1000 times larger than 10 to the power 12. That is the power exponential notation. It lets us compare huge quantities very quickly. Practice scientific notation. Now it's your turn to use scientific notation. Question number 1. Ants per human. Suppose we estimate 10 to the power 16 ants and about 8 multiplied by 10 to the power 9 humans. To find the approximate number of ants per person, we divide 10 to the power 16 by 8 multiplied by 10 to the power 9. This gives approximately 1.25 multiplied by 10 to the power 6, and 10 to the power 6 means 1 million. So that is about 1.25 million ants per person. Now let's try another. Question number 2. Flocks of birds. Suppose there are approximately 10 to the power 11 birds and each flock contains 10 to the power 4 birds. We divide 10 to the power 11 by 10 to the power 4, which gives us 10 to the power 7, and 10 to the power 7 is 10 million. So approximately 10 million flocks. Finally, consider the number of leaves on earth. If there are about 10 to the power 11 trees, and each tree has around 10 to the power 4 leaves. We multiply 10 to the power 11 multiplied by 10 to the power 4. Using the laws of exponents, we add the exponents. So answer is 10 to the power 15. So our estimate is approximately 10 to the power 15 leaves. Notice the beautiful shortcut here. When multiplying powers of the same base, we add the exponents. Say your age in a different way. Usually when someone asks your age, you answer in years. But what if I asked, how many days old are you? Or how many hours? Or minutes? Or even seconds? Let's meet Roxy. Roxy is 4840 days old. To convert days into years, we divide by 365. That gives approximately 13.3 years. But if we want hours, we multiply by 24. 4840 multiplied by 24 gives 1,16,160 hours. Now, let's look at S2. S2 is 4070 days old. That is approximately 11.2 years. But in hours, S2 has already lived 97,680 hours. And in minutes, that becomes 5,860,800 minutes. Now keep going. Multiply by 60 again, and we get the number of seconds, approximately 3.5 multiplied by 10 to the power 8 seconds. So, here is an interesting question. Your age hasn't changed, but the way we represent your age has changed dramatically. Years to days, days to hours, hours to minutes, and minutes to seconds. This is a great activity to do in pairs. So students, please calculate your own age in different units and explain each conversion step in comment box. What can happen in 1 million seconds? Now let's take a number we see frequently in mathematics. 1 million. 1 million seconds is written as 10 to the power 6 seconds. But what does that actually mean in everyday life? Let's convert it. 1 million seconds divided by 60 gives approximately 16,667 minutes. Divide by 60 again and we get approximately 277.8 hours, and divide by 24 and we get approximately 11.6 days. So here is the surprising part. 1 million seconds is only about 11.6 days. A number like 1 million sounds enormous when we hear it, but when we connect it to something familiar, like time, we understand its actual scale much better. Now think about 10 to the power 7 seconds. That is approximately 3.8 months or about 115 days. So, changing the exponent from 6 to 7 does not simply add 1. It makes the quantity 10 times larger. That is the key idea we are building toward. Can you think of something that could happen in about 12 days? What about 4 months? Comment in comment box. From months to years, 10 to the power 7 to 10 to the power 9 seconds. Now let's increase the exponent step by step. Start with 10 to the power 7 seconds. That is approximately 3.8 months or about 115 days. Now move to 10 to the power 8 seconds. that is approximately 3.17 years, and then to 10 to the power 9 seconds, that is approximately 31.7 years. Look at what happened. We moved from 10 to the power 7 to 10 to the power 8 to 10 to the power 9. Each time the exponent increased by 1, the quantity became 10 times larger. So, powers of 10 give us a very simple way to understand enormous changes in scale. Instead of writing every large number, we can simply look at its exponent. Now, let's make this interactive. Imagine we have event cards representing different time periods. Let's place them on a classroom timeline according to whether they belong closer to 10 to the power 7, 10 to the power 8 or 10 to the power 9 seconds. This helps us connect an abstract mathematical exponent with a real world sense of time. Exponential notation reveals deep time. Now we are going much further back in time. Let's look at 10 to the power 10 seconds. That is approximately 317 years. Move to 10 to the power 11 seconds. And we are talking about approximately 3170 years. Then 10 to the power 12 seconds represents approximately 31,700 years. These are periods of time that are difficult for us to imagine. That's exactly why scientific notation is so powerful. Instead of writing a number like 31,700 again and again, we can describe the scale using 10 to the power 12 seconds. The exponent acts like a quick label for the size of the quantity. When you see 10 to the power 12, you immediately know that you are dealing with a tremendously large amount of time. So remember, the exponent tells us the order of magnitude, the scale of the quantity. The bigger the exponent, the larger the number. From Earth's age to the age of the universe. Let's take this idea to an even bigger scale. We can use powers of 10 to represent enormous periods in Earth's history. For example, 10 to the power 16 seconds is approximately 317 million years. 10 to the power 17 seconds is approximately 3.17 billion years. Now consider the age of Earth. Earth is approximately 4.5 billion years old. In seconds, that is approximately 4.5 multiplied by 10 to the power 17 seconds. And the Milky Way is estimated to be around 13.6 billion years old, which corresponds to an enormous number of seconds. Imagine trying to write all those seconds out as ordinary numbers. It would be extremely difficult to read and compare them, but scientific notation allows us to put these enormous quantities onto the same mathematical scale. And this is why mathematics becomes a language for describing things that are almost impossible to imagine. Now, let's make this physical. Imagine a timeline across the classroom. Students, you can stand at different positions representing different powers of 10. This turns an abstract exponent into something we can actually see and experience. Use powers of 10 to make the unfamiliar to familiar. We have reached our final challenge. Let's take quantities so large that they are almost impossible to imagine. Suppose the observable universe contains approximately 10 to the power 24 stars. Now imagine counting one star every second. It would take approximately 10 to the power 24 seconds. That corresponds to roughly 3.17 multiplied by 10 to the power 16 years. That is an unbelievably long time, far beyond the age of the universe. Now consider the amount of water on Earth. The estimate is approximately 1.4 multiplied by 10 to the power 21 liters. If we imagine using a 200 milliliter glass and taking one glass every 10 seconds, the total time becomes an enormous number again. And this brings us back to the main idea of today's lesson. When quantities become extremely large, ordinary numbers become difficult to read, compare, and understand. Scientific notation gives us a compact way to represent their scale. The exponent tells us how large the quantity is. So, whenever you see a huge number, don't be frightened by all those zeros. Look at the exponent. The exponent is telling you the scale of the world you are dealing with. Before we finish, here is your exit ticket. Write one everyday example where scientific notation can make a very large quantity easier to understand, and be ready to explain your example to the class. Today, we started with something as simple as taking steps, and we ended up talking about the moon, populations, ants, seconds, Earth's history, and the universe. That is the beauty of mathematics. A small idea like a power of 10 can help us understand numbers far bigger than we can imagine. What do Google and Googleplex mean? Let me start with a number that sounds almost like a made up word. Have you ever heard the word Google? A Google is a very, very large number. It is written as 10 to the power 100. That means 1 followed by 100 zeros. Now you might think that is already an unimaginably large number, but mathematics has an even bigger one. It's called a Googleplex. A Googleplex is written as 10 raised to the power of a Google. In other words, the exponent itself is already 10 to the power 100. So, we are not simply talking about a big number anymore. We are talking about a number so enormous that writing it out completely is practically impossible. Here is the key idea. A Google is not just a huge number, it becomes the exponent in Googleplex, making Googleplex unimaginably larger. And here is a fascinating mathematical fact. The word Google was coined in 1938 by a 9-year-old boy named Milton Sirota. Later, the company Google chose its name based on this idea of an enormous scale of information. So, mathematics isn't just about calculations. Sometimes even the names of numbers have fascinating stories behind them. If a Google has 100 zeros, how many zeros would you expect in a Googleplex? Give your answer in comment box. Question number 2. Find the units digit. Now let's move from enormous numbers to a very clever question. Suppose I give you a huge power of 2. Do we really need to calculate the entire number to find its units digit? The answer is no. We can use a pattern. First, let's simplify the exponent. We have 4 to the power 32. which is equal to 2 to the power 2 bracket complete to the power 32 is equal to 2 to the power 64. So the expression becomes the question given in the slide. It becomes 2 to the power 224 divided by 2 to the power 64. Using the quotient rule for exponents, we subtract the exponents and we'll get the answer 2 power 2 to the power 160. Now comes the clever part. Look at the units digit of powers of 2. 2 to the power 1 ends in 2. 2 to the power 2 ends in 4. 2 to the power 3 ends in 8. 2 to the power 4 ends in 6. And then the pattern repeats 2, 4, 8, 6 and so on. So the units digit repeat in groups of 4. Our exponent is 160. Since 160 is exactly divisible by 4, there is no remainder. Therefore, we need the fourth number in the cycle, and the fourth number is 6. So, without calculating a gigantic number, we can immediately say that the units digit is 6. This is an important mathematical strategy. When numbers become huge, look for patterns instead of calculating everything. Pause your video and tell me in comment box what are the units digits of powers of 2. Let us discover the cycle before revealing the answer. Question number 3. Write each number as a products of powers. Now let's practice rewriting numbers using powers. The goal is not simply to calculate the number. The goal is to break it into useful powers. Example number 1. We have 64 to the power 3. We know that 64 equal to 2 to the power 6. Therefore, 64 to the power 3 is equal to 2 to the power 6 bracket complete to the power 3. Using the power of a power rule, we multiply the exponents and we will get 2 to the power 18. And we can also write this as 2 to the power 9 multiplied by 2 to the power 9. Why? Because when multiplying powers with the same base, we add the exponents. 9 plus 9 equal to 18. Example number 2. Now consider 192 to the power 8. We can break 192 into 64 multiplied by 3. And earlier we have seen that 64 equal to 2 to the power 6. We get 192 equal to 2 to the power 6 multiplied by 3. Raising this to the 8 power gives 2 to the power 48 multiplied by 3 to the power 8. Example number 3. Now look at 32 to the power minus 5. 32 can be written as 2 to the power 5. So 32 to the power minus 5 can be written as 2 to the power 5 bracket complete to the power minus 5, which is equal to 2 to the power minus 25. And we can split that further as 2 to the power minus 10 multiplied by 2 to the power minus 15. The main idea here is that Exponent rules allow us to break complicated expressions into simpler pieces. Once you recognize the powers hidden inside numbers like 32, 64, or 192, the simplification becomes much easier. Question number 4. Decide whether each statement is true. Now we are going to test our understanding. But instead of simply solving equations, we are going to decide whether mathematical statements are always true or never true. Let's take the first statement. A cube is always a square. Is this true? No. For example, 2 to the power 3 equal to 8 and 8 is not a perfect square. So this statement is never true in the general sense. Now look at n to the power 4 equal to n to the power 2 bracket complete to the power 2. This is always true. Why? Because n to the power 2 bracket complete to the power 2 equal to n to the power 2 multiplied by 2 is equal to n to the power 4. This is the power of a power rule. Next, n to the power 5 equal to n to the power 3 multiplied by n to the power 2. Again, this is always true because when we multiply powers with the same base, we add the exponents as 3 plus 2 equal to 5. Now, a to the power 3 multiplied by b to the power 3 equal to in the bracket ab bracket complete to the power 3. This is always true. The exponent can be distributed across the product and we can write a to the power 3 multiplied by b to the power 3 as in the bracket ab bracket complete to the power 3. Next, finally look at the statement 4 to the power 6 is divisible by 4 or 6. Be careful here. 4 to the power 6 is a power of 4. Being a power is not the same thing as saying the exponent is a multiple of something. So this statement is classified as never true according to the slide. The important lesson is don't just look at the numbers, understand what the exponent is actually telling you. Question number 5. Simplify using exponent rules. Now let's put all our exponent rules together. Part 1. Multiplication. We have 10 to the power minus 2 multiplied by 10 to the power minus 5. The bases are the same, so we add the exponents as minus 2 plus minus 5 equal to minus 7. Therefore, answer is 10 to the power minus 7. Part 2. Division. Now, 5 to the power 7 divided by 5 to the power 4. When dividing powers with the same base, we subtract the exponents as 7 minus 4 equal to 3. So, the answer is 5 to the power 3. Part 3. Consider 9 to the power minus 7 divided by 9 to the power 4. Again subtract the exponents as minus 7 minus 4 equal to minus 11. So, we get 9 to the power minus 11. Part 4. Power of a power. We have 13 to the power minus 2 bracket complete to the power minus 3. When a power is raised to another power, we multiply the exponents as minus 2 multiplied by minus 3 equal to 6. So, the answer is 13 to the power 6. Part 5. Combining variables. Finally, we have m to the power 5, n to the power 12 in the bracket mn to the power 9. First expand in the bracket mn to the power 9, m to the power 9, n to the power 9, and already m to the power 5, n to the power 12 given. Now combine like basis as m to the power 5 multiplied by m to the power 9 is equal to m to the power 14, and n to the power 12 multiplied by n to the power 9 equal to n to the power 21. Therefore, final answer is m to the power 14 n to the power 21. So, remember our three major rules. First, multiply, add exponents. Second, divide, subtract exponents. Third, power of a power, multiply exponents. These three rules can simplify many complicated looking expressions very quickly. Question number 6. Use 12 square is equal to 144. Now let's explore something interesting about squares. We know 12 square equal to 144. But what happens when we change 12 by dividing or multiplying it by powers of 10? Let's start with 1.2. Notice that 1.2 equal to what? It is equal to 12 divided by 10. So 1.2 square is equal to 1.44. The number was divided by 10, but when they square it, the result is divided by 100. Why? Because 12 divided by 10 to the bracket complete to the power 2 equal to 12 square divided by 10 square. Now let's go one step smaller. 0.12 equal to 12 divided by 100. Therefore, 0.12 square equal to 0.0144. This time the square is divided by 10,000, and 0.012 equal to 12 divided by 1000. Its square becomes 0.000144. So the pattern is becoming very clear. Now let's go in the opposite direction. If we multiply 12 by 10, we get 120. And 120 square equal to 14,400. That is 100 times 144. So here is our golden rule. When you multiply a number by 10, its square is multiplied by 100. And this idea comes directly from exponents rule, as 10 square equal to 100. That is the connection we want students to notice. Question 7. Circle the equal expressions. Now let's finish with a matching challenge. We have different looking expressions, and our job is to identify which ones actually have the same value. Look at the expression. 2 to the power 4 multiplied by 3 to the power 6. We want to rewrite it in a form that makes comparison easier. Notice that 2 to the power 4 can be written as 2 to the power 2 bracket complete to the power 2, and 3 to the power 6 can be written as 3 to the power 3 bracket complete to the power 2. Therefore, 2 to the power 4 multiplied by 3 to the power 6 equal to, in the bracket, 2 to the power 2 multiplied by 3 to the power 3 bracket complete to the power 2. So we have transformed the expression into a square. Now let's look at 18 to the power 2 multiplied by 6 to the power 2. Because both because both terms are squared, we can combine them as in the bracket 18 multiplied by 6 bracket complete to the power 2, and since 18 can be written as 2 multiplied by 3 to the power 2 and 6 can be written as 2 multiplied by 3. We can see how the same powers are being constructed. Therefore, the expressions identified on the slide as 2 to the power 4 multiplied by 3 to the power 6 and 18 to the power 2 multiplied by 6 to the power 2 are equal. The important rule here is a to the power n multiplied by b to the power n equal to in the bracket ab to the power n. So when the same exponent appears on two factors, we can combine them into one power. This is another example of how exponent rules allow us to recognize equality without calculating enormous numbers. Today we started with numbers so enormous that we could barely imagine them, a Google and a Googleplex. Then we moved into patterns, unit digits, powers, negative exponents, true or false, true or false statements, and finally algebraic expressions. The big message is simple. Exponents are not just about calculating big numbers. They are a shortcut for seeing patterns. Once we understand those patterns, even complicated looking expressions become much easier to handle. And that is the real power of mathematics. Question number 8. Which number is greater? Now let's move to question 8, where we have to compare numbers written in exponential form. We have three interesting comparisons. First, we compare 4 to the power 3 and 3 to the power 4. Let's expand them. 4 to the power 3 means 4 multiplied by 4 multiplied by 4, which gives us 64. And 3 to the power 4 means 3 multiplied by 3 multiplied by 3 multiplied by 3, which gives us 81. So clearly 3 to the power 4 is greater than 4 to the power 3. Now look at the second pair, 2 to the power 8 and 8 to the power 2. 2 to the power 8 is 256, while 8 to the power 2 is only 64. So here 2 to the power 8 is greater. And now comes the really interesting one, 100 to the power 2 versus 2 to the power 100. 100 to the power 2 is just 10,000, but 2 to the power 100 is an enormous number. In fact, even 2 to the power 10 is already greater than 1000, and raising 2 to the power 100 makes it astronomically larger. So the winner is clearly 2 to the power 100. The important idea here is we cannot compare powers simply by looking at the base or the exponent alone. We need to understand how both affect the value. Question number 9. How many digits does the ID need? Now imagine a dairy company that needs to uniquely code 8.5 billion packets. The question is how many digits should each code contain? Let's think about 9-digit code first. A 9-digit code can range from 9 times 0 to 9 times 9. That gives us 10 to the power 9 or 1 billion possible codes. But our company needs codes for 8.5 billion packets. So 9 digits are definitely not enough. What happens if we use 10 digits? A 10-digit code gives us 10 to the power 10 possible combinations, which is 10 billion. And 10 billion is comfortably greater than 8.5 billion. Therefore, the answer is 10 digits. This is a greater real-life application of powers of 10. Computer systems, product IDs, phone numbers, and identification systems all depend on this kind of counting. Next question, question number 10. Numbers that are both squares and cubes. Here is a beautiful connection between squares, cubes, and exponents. Can a number be both a perfect square and a perfect cube? Yes. Take 64. We know that 64 equal to 8 square and also 4 to the power 3. So 64 is both a perfect square and a perfect cube. But why does this happen? The exponent of a perfect square must be divisible by 2, while the exponent of a perfect cube must be divisible by 3. The smallest number that is divisible by both 2 and 3 is 6. That means numbers of the form n to the power 6 will be both perfect squares and perfect cubes. For example, 1 to the power 6 equal to 1, 2 to the power 6 equal to 64, 3 to the power 6 equal to 729, 4 to the power 6 equal to 4096. So remember this beautiful rule. Every sixth power is simultaneously a perfect square and a perfect cube. Question number 11. Alphanumeric local codes. Now let's connect mathematics with something students see every day, passwords and local codes. Suppose each local code contains 5 positions. Each position can contain a digit or an uppercase letter. So, for every position, we have a certain number of choices. Because repetition is allowed, we can use the same character again and again. Therefore, we multiply the number of choices for each of the 5 positions. This gives us a total of 60,466,176 possible codes. That is more than enough to provide unique codes for a school. The key mathematical idea here is the multiplication principle. If one position has several choices and each position is independent, we multiply the choices together. So, a simple local code becomes a powerful application of mathematics. Question number 12. Sheep and goats together. Now we have a very important question about adding large numbers. Suppose the number of sheep worldwide is approximately 10 to the power 9 and the number of goats is also approximately 10 to the power 9. If we want the total population, should we write 10 to the power 18? Absolutely not. We are adding the populations, not multiplying them. So we write 10 to the power 9 plus 10 to the power 9. Since both terms have the same power of 10, we can factor out 10 to the power 9. That gives us 2 multiplied by 10 to the power 9. So the answer is 2 billion or 2 multiplied by 10 to the power 9. This is a very important point to remember. When adding numbers in scientific notation, we do not add the exponents. Exponents are added when we multiply powers with the same base, not when we simply add the numbers. Question number 30. Write each answer in scientific notation. Now let's apply scientific notation to some fascinating real life quantities. First, clothing. If one person has 30 items and there are approximately 8 billion people, we get 30 multiplied by 8 multiplied by 10 to the power 9. That becomes 2.4 multiplied by 10 to the power 11 pieces. Next, honeybees. We have 10 to the power 8 colonies with approximately 5 multiplied by 10 to the power 4 bees per colony. Multiplying them gives us 5 multiplied by 10 to the power 12 bees. Now look at bacterial cells. If each person has approximately 38 multiplied by 10 to the power 12 bacterial cells and there are 8 multiplied by 10 to the power 9 people, the result is 3.04 multiplied by 10 to the power 23 cells. And finally, let's calculate the amount of time spent eating in a lifetime. When we multiply minutes, meals, seconds, days, and years, we get approximately 8.8695 multiplied by 10 to the power 7 seconds. The main skill in all these examples is converting huge numbers into scientific notation, which makes them much easier to read, compare, and calculate with. Question number 14. What was the date 1 billion seconds ago? Now for our final challenge, and this one is really fascinating. The question is, what was the date 1 billion seconds ago? First, write 1 billion as the power of 10. 1 billion equal to 10 to the power 9 seconds. Next, we need to know how many seconds are there in 1 year. 60 multiplied by 60 multiplied by 24 multiplied by 365 gives us 31,536,000 seconds per year. Now divide 10 to the power 9 by 31,536,000. This is approximately 31.7 years. So, if we could make roughly 31 years and 259 days from 17 August 2026, we reach approximately 1 November 1994. Isn't that amazing? A number that looks simple, 1 billion seconds, actually takes us more than 3 decades into the past. And remember, the exact date can shift slightly depending on the exact time and leap years. So, mathematics isn't just about calculations, it can actually help us travel through time. Excellent work, students. In these questions, we have seen how power of 10 and exponents help us compare huge numbers, create identification systems, understand squares and cubes, count possible codes, work with populations, express enormous quantities in scientific notation, and even calculate a date from 1 billion seconds ago. This is exactly why understanding exponent is so powerful. They allow us to make sense of very, very large numbers in a simple way. So, here students, we have concluded the chapter number 2, power play.